In this video, we'll create a MicroBlaze soft microprocessor on a BASYS3 board and we'll add I/O and UART modules to form a basic microcontroller. We'll be using Vivado and Vitis development platforms. Now let's see how we will organize this project. We'll start our project in Vivado and we will be creating our block design by adding intellectual properties or IPs for short. In this particular project, we will be adding clock, the MicroBlaze CPU, push buttons, LEDs, and UART. The next step will be creating an HDL wrapper and generating a bit stream which will automatically run the synthesis and implementation. Our final task in Vivado will be to export this design as hardware platform. At the second phase of the project, we'll jump to Vitis IDE and create an application project by selecting the hardware platform that we just created in Vivado. Then we are going to create our code for our application project and then we will be building it. Finally, we'll connect our BASYS3 board and run our application project as launch hardware, and we'll see our C code running on the soft platform which we implemented inside the BASYS3 FPGA board. In the video, I did not remove the difficulties and errors that I came across and showed how to correct them so that you'll better understand the things that we need to pay attention to. So let's start Vivado immediately since we have lots of things to do. First, we are going to create a new project in Vivado. Let's click on Next. We are going to change the project name. We can name it as BASYS3 MicroBlaze. Click on Next. We also check project is an extensible Vitis platform. Click on Next. Now we are going to go to Board section and then we are going to click on Refresh to get the updated catalog. And we will search for our BASYS3 board. And we select that one and then we install that by choosing the status cell. And then we select it once it's installed and click on Next. This is the summary of our project. We see our board here. We click on Finish. Okay, now we are in Vivado and we are going to create a new block design in the IP integrator part. We are going to leave the name as Design 1. And we can see the Boards tab. When we extend that, we see the modules like System Clock, Flash, Push Buttons, 7-segment display, anodes and segments, 16 LEDs, and also 16 slide switches, P mode connections for P modes. One is the ADC. First, we are going to create a system clock. We're going to click on OK. And we are going to click on Run Connection Automation. Click on OK again. When we double click on that, we can see the output clocks, 100 MHz selected. And we are going to add our MicroBlaze soft microprocessor. Again, we are going to click on Run Block Automation. And this is the summary of our microprocessor. Pay attention to that local memory, 8 kilobytes. That's going to create a problem for us in the future. Now you can see that we've implemented the clock and also the reset signal. We are going to add the USB UART by Connect Board component. We are going to select UART Lite and click on OK. And it's also added automatically to our diagram. We can click on Run Connect Automation again, leave the default settings. Now what we are going to add is the LEDs. We are going to select the 16 LEDs. We are going to again right click on it, connect board component, leave the default settings as GPIO. and it's being created. This was created automatically, the LEDs, but now we are going to add the buttons manually. We are going to change the name of the block to GPIO_LED. Click on enter and it's renamed. Now let's add AXI GPIO. That's the wrong writing, so AXI space GPIO, we can find it in the list. So now we are adding it manually as advised in the Digilent tutorial, and we can rename this one as well to buttons and click on enter. You see that its name has changed. Now since we added this manually, we are going to first make this GPIO external by right clicking on it, choosing make external, and we are going to need an XDC file. We are going to select sources constraints, new, add sources, and create constraints file. Click on next. We are going to create file. We are going to name it. We can name it whatever we want. BASYS3 master XDC. Doesn't matter. So we can click on finish. But now we need to create our constraints file. Let's choose the XDC file, double click on it, it's empty. Now we are going to get the master XDC file. You can get this file from Digilent's website. We are going to copy and paste it. However, we need to do some modifications on that. You see that some of them are already commented out, but we are going to be using the buttons section. So we are going to disable the comments here. Pay attention to this. We have 5 buttons on BASYS3. However, right now we are going to rename it to BTN buttons, okay? Okay, we can leave it as it is. In the XDC file, we are going to rename these as advised in the Digilent tutorial, okay? We are going to name it button_3_IO, and we are going to give the index. You see that we have 5 buttons in the XDC file. However, you are going to see that the center button is reserved for reset. So the thing that we are doing right now won't work, but let's leave it as it is. Let's continue like this. So we will have 5 buttons defined, starting from index 0, ending at 4. Button right, you see that words right there, button right, button down. So the last one is down button. Okay, we updated the XDC file, we saved it. And we can see the IP configuration of the buttons. We need to change the GPIO width. We need to make it 5 because we created 5 buttons in the XDC file. So it's matching. You see that from 0 to 4 in GPIO_IO_I. We select all automation and click on OK in the Run Connection Automation box. OK. Now our design seems complete. We click on Validate Design, and it's completed as well. Now we are going to generate bit stream. First, we are going to create HDL wrapper, and we are going to select Let Vivado Manage Wrapper and Auto Update, and click on OK. creating this Verilog file design one wrapper. It's also complete. Now we can click on generate bitstream. It's going to run synthesis and implementation first. We are going to click on yes. Okay, we select the default settings. This is going to take a while. I trimmed the sections, so don't expect it to be as quick as in this video. So it's going to take some time. Okay, it's running multiple block runs. You can see on the upper right, and the bitstream generation has failed. So let's try to understand what the problem was. Let's check the log. In the messages, we see that there seems to be a problem with the XDC file. Actually, this summarizes that we need only the section related with the buttons. The rest should be commented out, or you can delete them as well. So we are going to comment these sections out. We'll leave the buttons only, and also the rest of the file. Even though some portions are already commented out, let's comment them out once again. Okay, now we can try to generate the bitstream once again. It's going to do the synthesis and implementation first. And it says synthesis complete, initializing design, running op design. You can see it on the top right corner, and bitstream generation has again failed. So actually we had already mentioned this was going to create a problem for us. So the first button, which was the center button, was already reserved for reset. So we need to comment it out, and we need to shift the index accordingly. So the first one will have the index 0, the second one 1, 2, and 3. So let's change them accordingly. And we need to set the GPIO width as well, since we reduced it from 5 to 4. We set it to 4, click on OK. We need to make sure that the last two lines are matching as well, IO3, IO3, and save it, and try to generate the bitstream once again. So it's going to go through the same steps. This is going to take longer in real world. As I said, I trimmed most of the sections. So if you follow up right corner, you see the progress. And finally, we had generated the bitstream successfully. After generating the bitstream, we are going to export the platform. We are going to click on next, and we are going to choose hardware. We will check the include bitstream, and we are going to click on next. Here we have the platform properties. We can change the name, or we can leave it as default. So in the next one, we have this XSA file name. So we can leave the name as default. We can have the file name as design1 wrapper. And this is the summary of the hardware platform. We can click on finish. However, we are receiving these errors during the generation of the platform. We can see that in the platform setup tab, we have some exclamation marks in the AXI port and in the clock. Let's try to tick in the AXI port and choose our clock out in the clock out and set is default to true for the clock. This time, let's try to generate the bit stream once again. So it's again doing the synthesis design and etc. You can see those on the upper right corner. So bitstream is successfully generated. Let's go back to export platform once again. Let's click on generate output products 2. Let's see the progress. We again click on next in export hardware platform. We choose hardware, click next, include bitstream once again, click next again. So we click yes, leave the default settings, click on next. We again click on next. This is the summary, click on finish. Unfortunately, we receive errors again. So what we are going to do is we are going to uncheck all boxes in the AXI port section, and we are just going to leave the setting with the clock, and we are going to validate the design and then try to generate the bit stream once again. You see that our diagram is okay, and we generate bit stream. And our bit stream is successfully generated. Now we can try to again export our hardware. Click on next, choose hardware, click next, include bitstream, click next, leave the default, next, and design one wrapper, next, and this is the summary, and we are going to click on finish and hope that this time it's going to be okay. And fortunately we didn't get any errors, some warnings, but our hardware is exported. Now we need to install Vitis, and in order to do that we are going to click on Add Design Tools or Devices in the Help menu, and it's going to launch the unified Xilinx installer for us. We are going to click on Next to the Welcome screen, and we are going to enter our email address and password that we used previously to install Vivado, and we are going to select Vitis Unified Software Platform. We are going to upgrade our installation to this, and in this window, I suggest that you choose only the series that you are going to work with. So I chose 7 series and I didn't select the others because it's going to require a large number of space. Right now it requires 46 gigabytes, and we are going to click on install, and it's going to start installing Vitis for us. Once Vitis is installed, we can launch it from Launch Vitis IDE in Vivado, or you can choose from the start screen. Once it's being launched, it's going to ask for a workspace. We can choose the default setting and click on launch. And in the workspace, we can extend this window. There are several options. We are going to choose create application project, and we are going to click on next. Now we need to choose the XSA file that we have created. XSA stands for Xilinx Shell Architecture, and we are going to browse and locate our XSA file that we created in Vivado. And once it's selected, we can continue by clicking on next. And we can name our application project like MicroBlaze or MicroBlaze 2. and we can click on next to continue. We will leave these default settings, and now we are going to choose empty application C or empty application C++ and click on finish. And now we are in Vitis, and first thing that we will need to do is to create a new file. We are going to name it main.c, and once it's created, we are going to go to the Digilent's tutorial page and copy the main.c file. In this page, there is a very nice description about this main.c file. You can check it. I won't be explaining in detail, and we are going to paste it here. The modification that I will do is to extend this LED mask to 16 bits because the BASYS3 board has 16 LEDs on it. And we can save this one. And now we are going to right click on mblaze_system. We are going to click on build to build our project. And let's observe the console for the errors and warnings. In the end, we can see that we have an error. When we look at the error, we see that this is a memory problem. To solve this problem, we should go back to Vivado and check the address editor. You can see that both the DLMB and ILMB were 8K in the beginning, so we should increase them up to, let's say, 32K. This is because the Xilinx printf function is consuming more memory, so either you comment it out or use these settings. Assuming that we have done the memory upgrade in Vivado and generated the bit stream and exported the hardware once again, now we are in Vitis once again and we are connecting to our board. Our board is at COM9. We can check it in device manager, so your COM port can change for sure. And the baud rate is going to be 9600 baud. And what we are going to do is we are going to right click on our system and we are going to run as launch hardware. Before that, we should build our application as well. So after running it as hardware, we can see that in COM9 we are going to receive this message entered function main, which was already specified in the main function in our main.c file. And you can see that once we press the buttons up, down, or left or right, we can see that all of the LEDs, 16 LEDs, are turning on. And let's change this LED mask. So let's have the middle 8 LEDs off. In order to do that, we change those with zeros. We save it and we are going to build our application once again. Let's click on build. Once it's built, we are going to again run as hardware. Let's reset our terminal. By the way, I'm using PuTTY for the terminal. Let's right click and click on run as launch hardware once again. Let's click on relaunch. Okay, we are going to get the message again. We had an error, so let's try to rerun our application. We can use this green play button, run as launch hardware. And again, we have entered function main, so let's try to press the buttons. You can see that the 8 LEDs in the middle are not on when we press the button. The 4 LEDs on the right and the 4 LEDs on the left are on when we press the button. So let's try to change the while one loop. Let's add another else if here. And for example, let's say that if data is equal to binary 1000, we should indicate that it's binary by putting 0b in the beginning of it. So we are going to print out to UART for sure. By using the Xilinx printf function, we will say left button pressed, but we should check if it's going to be the left button. However, we should also modify the first if clause because we need to make sure that the other three options are there, the other three button presses. So we are going to OR them. With 0B0010 and also OR 0001. Okay, we can save this, modify the last one as well, 0001. We can build our application once again. And then we can again use run as, launch hardware, relaunch, okay, we are going to run it once again. Okay, we again entered function main, just check the putty screen. So once we click on up button, nothing happens. Right button, nothing happens. Left button, nothing happens. So that's actually the down button pressed, but we see left button pressed. So we have chosen the wrong mask. So we can write down button press. So you can go back to the XDC file and check by yourself. You can see that the fourth index was the down button. So you can relate it with this. So once we build it again, reset our terminal and run as launch hardware once again. Once it's launched, we are going to get our message again, entered function main. So let's press the buttons. So when we press the button, the down button, we are going to see on the screen down button is pressed.